Good morning, class. Good afternoon, class. It's that time again. It's your boy, Math Man McCutcheon. I'm coming at you live. Well, not really. Okay, pre-recorded from my office/dining room with the second distance learning notes. Okay, so we are still talking about rates and change of limits. We're still in section 2.1 of the AP Calculus textbook, but we're going to dive a little bit deeper today. Now, last time we talked about what a limit was. A limit was a real y value that our graph was approaching as x approached a real value as well. We saw that as long as plugging in that x value doesn't give you any kind of discontinuities, aka dividing by 0, then that's literally what you did. You just plugged the number in. You also saw me do limit as, where are we? Here, I'll find it, I'll pull it up, boom. The limit as x approaches 0 of sine x over x, and we saw that it equals 1. In fact, we also saw in general that if you put a value here and here, like 3 and 4, then the limit would just be this value over this value, 3/4. So right now it's 1 because there's a 1 in front of this x and a 1 in front of this x. Okay, so let's dive a little bit deeper. Last time we practiced some of the pretty understandable rules of limits, but we didn't get to the product rule. Mr. M, this looks like a fraction. Why isn't this quotient rule? Well, it's not the quotient rule because I literally can't plug in 0 again. See, if I plug in 0, well, that makes me divide by 0. Not to mention tangent of 0, yeah, it's also undefined. So you can't plug in 0, which means we can't use the quotient rule. So how do we use the product rule? Well, let me break it down for you. Literally, break it apart. We're going to use some trig skills. The limit as x approaches 0 of tangent x over x. This could be thought of as the limit as x approaches 0, wow, that's a horrible arrow, of tangent x times 1 over x. Well, crap. That doesn't help this, has it? Yeah, I still have a discontinuity here and here, so what do? Why don't we not say tangent x? Why don't we say sine x over cosine x? There. Now, the way it sits, I still have some discontinuities, because I can't plug in 0 right here. You know what I just realized? I think I said that tangent is undefined at 0 way back at the beginning of the video. Clearly in need of some caffeine. Tangent is not undefined at 0. My apologies. Anyway, you still can't divide by 0. I'm right about that, so meh. Okay? Anyway, see this multiplication? The nice thing about multiplication is it doesn't care about order, does it? I mean, not a times b is the same thing as b times a, right? I mean, if that's the case, then you know what I'm gonna juggle this up a little bit. Whoa! I wrote x approaches x. Fixed. You were probably sitting right there yelling at your screen. This guy doesn't know how to do math. I'm smart, I promise. The limit as x approaches 0 of, time to play with the order of multiplication. Why don't I say sine x over x times 1 over cosine x? There. I just switched these two things because cosine x times x is the same thing as x times cosine x, right? Yes, Mr. M? Okay, good. And now we can see that the product rule works because I can split this up into two limits being multiplied together. And guess what? This thing right here, we have a rule for this. It equals 1. Remember I told you it was important, you're going to need to memorize it? And, well, cosine of 0 is 1, so I don't have a discontinuity here. This literally says 1 times 1. which equals 1. Mic drop. Like we're done, right? No, okay. Well, the first question's done. There. If you don't believe me, you're welcome to put it up on Desmos or your graphing calculator and you'll see that it's true, but it's kind of hard to argue with the math. So yeah, your trig skills, still important. You're not allowed to forget them. All right. The title of this question kind of gives away the punchline. It says exploring a non-existent limit, but it says to use a graph to show that this limit doesn't exist. You can't plug in 2 because you have a discontinuity. So let me grab handy dandy grapher and avoid all the bright spotlights above me and the shadow of the document camera. There we go. Okay, on. Y equals. You've seen this trick before. Let's see what happens. Oh, by the way, my X scale goes by ones. The Y scale is unimportant. God, I can't wait to see what happens. Whoa, shot down at X equals 2. Holy cannoli. What an interesting shape. I said off. Let me sketch it out real quick. Picture not drawn to scale, of course. You knew I was going to say it. You knew it was coming. Vertical asymptote right there. And you might not remember it, but way back, quarter 1 or 2, we talked about in behavior asymptotes, and we said that you could look at the degrees of the top and the bottom. See, x to the third over x is actually x squared. So you didn't know it, but this graph also had a parabolic asymptote. And then our curve followed it like this. Come on, blue pen, don't fail me now. Hugs it that way and hugs it that way. Okay, so that was the picture, give or take, some deficiencies in my drawing, but that was the image. So what's going on at x equals 2 is the real question. Now, yesterday, the day before yesterday, I don't know, whenever you watch the last set of notes, how about we say last time, when I was doing limits, you saw me approaching x values from both sides. You see, the idea of both sides is really, really important because as I approach the x value 2 from the left of 2, my y values, they shoot down to negative infinity. But as I approach x equals 2 from the right of 2, my y values shoot up to positive infinity. Basically, the graph points in 2 different directions close to x equals 2. I mean, I can't say at x equals 2 because it doesn't exist at x equals 2, so it's close to x equals 2. So we say limit does not exist. There you go. See, what we've done here is we've kind of sort of defined what a limit actually is. I mean, last video I showed you approaching x's from both sides, and I was very careful to do that. Well, this is why. So what that leads us to is the concept of a one-sided or two-sided limit. So sometimes the values of a function tend to different limits as x approaches a number. Like you just saw up here, as x got close to 2, our graph went in 2 different directions. One side went up, one side went down. When this happens, we call the limit of f of x as x approaches c from the right-handed limit, and the limit as x approaches c from the left, the left-hand limit. So we have here is the concept of a right-hand limit and a left-hand limit. And because we have 2 new concepts, we need 2 new symbols. Boom, baby, here they are. It's kind of hard to see, so I will emphasize it. That is a little plus sign right above that C. That little plus sign right above the C means C and a little bit more, which means just to the right of C. This says the limit as x approaches c from the right. It doesn't mean you're going to the right. It means you're just to the right of value c. And the left-handed limit, again, it's really hard to see, so I'll emphasize that is a minus sign up there. That's the left-hand limit. That means the limit as x approaches c from the left. Again, you're not going to the left. It means you're just a hair to the left of value c. Time to take some old knowledge off the shelf. I'm talking way, way back in the second week of school. We introduced this thing, the greatest integer function. You don't believe me? I got lesson 3 right here. Pow! Let me see. Oh, see, lesson 3. Told you. Let's flip her over. And boom, there it is. Integer function. Get out of your notes. So there it is. Anyway, I can't remember not if I showed you this symbol for the greatest integer function, this pair of brackets, but get used to it. It's calculus people like to use it. Just to remind you what it is, the greatest integer function only returns integers that are less than or equal to the x you were plugging in. So if you plug in the value x equals 1.2, you get the y value of 1, because 1 is the largest integer that is less than or equal to 1.2. You see, the greatest integer function is full of jump discontinuities. Basically, you have a jump discontinuity at every single integer. Because of this, it has different left and right-handed limits. So let's find the limit as x gets close to 2, but from the right of 2. So it looks like this. You go, okay, getting really close to 2 from this side. Look at what your y values are doing. You look directly above where you're, quote-unquote, standing on the x-axis. You're up here. Well, as x got closer and closer to 2, y got closer and closer and closer to, you guessed it, 2. So as x approaches 2 from the right of the greatest integer function, our limit equals 2. Our right-handed limit is 2. But if you approach x from the left, you need a couple different colors here. If you approach 2 from the left of 2, meaning you're still going towards 2, but you're left of that number, you look directly above where you are. I can't tell if you can tell that that's a purple pen. Well, it looks blue on my camera. Well, it's purple. Anyway, this is green. So look directly above my purple arrow. I promise you it's purple. Look at what your y values are doing. As your x is getting closer to 2, your y's are getting closer to this open dot. And remember from the last video, I said the function doesn't have to actually exist there for that to be the limit. And this is a prime example of that. Because the limit as x approaches 2 from the left of my integer function is 1, even though the graph doesn't exist there. See, if you ask me what is the limit as x approaches 2, you kind of have a conundrum on your hands because there is technically 2 different answers. So what you'd have to tell me is that limit doesn't exist at x equals 2. But the limit to the left of 2 exists and the limit to the right of 2 exists. Oh, well, looky there, a box that's talking about one-sided and two-sided limits. Sometimes we say the limit as x approaches c of f of x is the two-sided limit, specifically because I didn't tell you if it was on the left or the right. So if I don't tell you it's on the left or the right, you have to say it is the two-sided limit. A function has a limit as x approaches c if and only if. A limit exists if and only if the right-hand limits and the left-hand limits are equal. So you have to say that a limit doesn't exist if the left and right limits are not equal. If the left and right limits are equal, then the function has limit L. And that idea is going to come up more in the future. It actually tells us something pretty neat. Something that earlier in our year, I did my best to describe to you, and I said, when we get into calculus at the end of the year, I'll be able to give you a stronger definition. It's coming. Okay, so let's do this last bunch of examples and we'll call this video a lock. It says use the graph to the left to evaluate each limit and draw some conclusions. And it doesn't mean literally draw, it just means, just to think about some stuff. Okay, I have 4 pen colors, but this picture is going to get rather colorful if I use them all, so you're just going to have to follow along with me with my pencil tip. Okay. Let's figure out what's going on at x equals 0. Well, our graph doesn't exist to the left of x equals 0, so we can only talk about the right-handed limit. So as x is getting closer and closer and closer to 0, approaching it from the right, your job is to be on the curve. I know it's straight, but it's called a curve. Your job is to be on the curve approaching what y value. So as my pencil drifts left and you were writing this curve, you'd be getting closer and closer and closer to that value, 1. So the right-hand limit at x equals 0 is 1. Let's talk about what's going on at x equals 1. Got this nasty jump discontinuity right here. So let's specifically say to the left of 1. So I'm approaching 1 from the left side of 1. If you were writing the curve, you'd be up here, getting closer and closer and closer to the y value of 0. Now you can't actually hit it because that's a jump discontinuity, but that is the goal. Remember, the point doesn't have to actually exist for it to be the limit. Let's approach x1 from the other side. Let's approach 1 from the right side of 1. So we're here and we're heading towards 1. While I'm doing this, your job is to be writing this curve approaching y value 1. So what is the limit as x approaches 1? Well, because you're forced to say from which side, you just go ahead and say does not exist. Because the left-hand limit and the right-hand limit are not equal. Okay, let's talk about what's going on at x equals 2. Let's approach 2 from the left. So I start somewhere over here to the left of 2, and I get closer and closer and closer to 2. And as I get closer and closer and closer to 2, the y values get closer and closer and closer to 1. No, it won't actually hit that point. It's another jump discontinuity, but that is the goal. What if we're getting close to 2 from the right? Oh, you can't see the picture. Drifting closer and closer and closer to 2 from the right side of 2. You're riding the curve, you're getting closer and closer and closer to the y value of 1. So the left-hand limit is 1, the right-hand limit is 1. So then what is the limit? 1. I'm trying to find last video. We had this example in the last video. You see, here we had a jump discontinuity in our last video. The limit was 2 because the left limit was 2 and the right limit was 2. The actual value is 1, but who cares? The goal we were trying to crash into was 2. Okay. Let's talk about x equals 3. Uh-oh. Uh-oh. You can't see that part of the notes and the picture at the same time. Unless I do this. Did that work? Focus, focus. Yep, that'll do. We're pretty good now. Can I get it all in there? Darn close. All right, well, we'll just have to use our imagination for the last one. Okay, x equals 3. Approaching 3 from the left. Approaching 3, approaching 3, approaching 3. Y values approaching, approaching, approaching 2. How about approaching 3 from the right? Getting closer to 3, closer to 3, closer to 3. Y values getting closer to 2, closer to 2, closer to 2. And just like you saw at x equals, we'll drop my pencil, just like you saw at x equals 2, because the left and right hand limits were equal, that was the limit overall. That was the same as the two-sided limit, so same thing is happening here. Because as I got closer to 3 on both sides, my y values got closer to 2 from both sides. 2 is the two-sided limit. The one that we're going to barely be able to squeeze into the bottom says the limit as x approaches 4 from the left because the graph doesn't exist to the right of 4. So you're getting closer to 4 from the left, closer, closer, closer. You're riding the curve. Y value is getting closer and closer and closer to 1. And the last example says non-integer values of x. So x is approaching any number that is not an integer. I don't care. Pick one. How about 1.5? That's not an integer. Well, at 1.5, I would get this y value. How about 2.5? I'd get this y value. How about 3.5? I'd get this y value. Basically, what we're getting at here is the only time I had any issues, if you're looking at the picture, were at the integer values. So that means I actually don't have a problem with plugging c into the function at a non-integer value. So then what is the limit as x approaches any constant that's not an integer? It's whatever y value you get when you plug that number in. Ta-da! Real mic drop this time. I hope you enjoyed. As usual, shoot me any reminds if you're confused about anything. And this homework assignment will be DL number 2 on my math lab, distance learning number 2. Now, the way it works is I can only pick questions from another textbook, the AP Calculus textbook, if I include at least one question from our textbook. So I'll be picking like the first question of every homework set will have to come out of our textbook. Sometimes it'll be review, sometimes it'll be pertinent, sometimes it'll be absolute nonsense. Just get that question right, okay? And the rest of them, the rest of them will come from the AP Calculus material. Hope everybody's still doing well and not going stir crazy. I'll be seeing you soon, fingers crossed, hopefully.